Okay, well, in this video, we're going to introduce trigonometric functions. Now we have already discussed in a previous lesson trigonometric ratios in a right triangle and trigonometric ratios in the unit circle. However, here in this lesson, we're going to look at trigonometric ratios as functions. So we're going to be graphing them on a coordinate system. So over here, the horizontal axis would actually be represented by the angle in radian. However, the vertical axis would be representing the function we're modeling, which in this case we're starting with f of x equals to sine x. So over here, y is in fact equals to sine x. So you can actually see that the curve of sine x in fact has this sinusoidal shape that alternates between -1 and 1. So if we were to just make a sense out of the shape of the curve, we're going to have to refer back to the unit circle. Now we know that in the unit circle, the coordinate system we introduced there, the orthonormal system, has its vertical axis that represents sine and the horizontal axis that represents cosine. So in fact, any point on the circle would have an abscissa equal to cosine of the angle it forms. So over here, the abscissa of this point would in fact represent cosine of the angle it's forming, and the ordinate would be sine of the angle it's forming, the horizontal axis. However, if we were to make sense of the shape of the curve of y equals to sine x, now over here at this point on the unit circle, the angle is 0. So, and the y value or the ordinate of that point is 0. Consequently, sine of 0 is 0, and this is why you would actually notice that the function passes through the origin. However, as the angle increases inside the first quadrant between 0 and pi over 2, so you'd notice here that between 0 and pi over 2, the sine function is in fact increasing until it reaches y equals to 1 at pi over 2, and on the unit circle, the angle or the point corresponding to an angle of pi over 2 or 90 degrees has in fact an ordinate equals to 1. So sine of pi over 2 is 1. And then as we continue across the second quadrant from pi over 2 pi, you notice that the angle is in fact decreasing in value, but symmetrically with respect to the values in quadrant 1. So this is why you'd notice that in 0 pi over this interval, the curve is in fact symmetrical with respect to pi over 2. Until finally it reaches 0 at pi, the ordinate of this point. This is where pi lies on the unit circle. So the ordinate of this point is in fact 0. So over here, that sine function in fact intersects the x-axis again at pi. And over here, as the angle moves to quadrants 3 and 4, in quadrants 3 and 4, sine is negative. So this is why the curve, in fact, is now below the x-axis. And over here, it keeps decreasing in value across quadrant 3 until it reaches -1 at 3 pi over 2. So this is the angle corresponding, or this is the point corresponding to an angle of 3 pi over 2 until it reaches y equals to -1 there. And then, while keeping its negative value, it starts increasing again until it reaches 0 again at 2 pi. So in fact, over here, the interval from 0 to 2 pi represents the behavior of the function across the unit circle as the angle opens from 0 all the way to 2 pi. So it represents the behavior over a full turn on the unit circle. However, we know that we can keep on going and making more full turns. So this is why the curve of sine would actually repeat infinitely. However, if we were to study the same behavior of the function, but if the angle moves in the negative sense, that would actually give us the behavior of the function for negative values of x, or the angle in this case. And of course, since we're dealing with oriented angles here, we can keep going in infinite number of full turns on the trigonometric circle. So consequently, the curve would actually keep on going infinitely, keeping the sinusoidal shape and ranging or alternating between -1 and 1. And as you recall in a previous lesson when we were discussing oriented angles and principal measures, we in fact discussed the fact that sine and cosine are 2 pi periodic, which means that the values of sine and cosine repeat every interval of length 2 pi. So in order to make more sense of that, if you remember, we did say, for example, that if sine of pi over 3, for example, is square root 3 over 2, then sine of 7 pi over 3 would still be square root 3 over 2, because pi over 3 and 7 pi over 3 differ by 2 pi, differ by a period of the function. Similarly, if we were to consider sine of pi over 3 plus 4 pi, which represents 2 full turns, the value of sine would actually repeat. In order to make sense of that, when we actually mention that even though the two angles have the same sine, but the two angles are in fact different, they're not the same angle, even if on the unit circle they land at the same point. If pi over 3 is here, then pi over 3 plus 2 pi would actually go back to the same point, leading to the same cosine and sine, since sine and cosine represent the coordinates of the point, so landing on a point would lead to the same coordinates. However, the angles are different, and in order to make sense of that, we can actually see this on this coordinate system where we're modeling the sine function. For example, if you look here, this is the angle corresponding to -3 pi over 2, you'd notice that over here y is equals to 1, which means that sine of -3 pi over 2 is equals to 1. However, if we move by an interval of length 2 pi, so if we move by an interval of length 2 pi, you notice again that at pi over 2 here, y again is 1, and sine of pi over 2 would in fact be equals to 1. So pi over 2 and -3 pi over 2 are different angles. On this number line, they lie on different and complete different places. However, they do have the same value of y. So keep in mind that whenever we do actually add or subtract full terms, or add two multiples of 2 pi or subtract multiples of 2 pi from an angle, the value of sine or even the value of cosine would actually repeat. You would end up with the same values. However, the angles you're dealing with would be different angles. Now over here, as you can see that there are no restrictions on the domain of this function. X can be any real number, so any real number would actually have a sine value. So over here, X belongs to R. There are no restrictions on X for sine. So consequently, the domain of the functions are real numbers. However, regarding the range, you'd notice that the y value alternates between -1 and 1. So consequently, that leads to y being between -1 and 1. So the range of the function is the interval -1, 1. And we already know that sine and cosine are in fact functions that are between -1 and 1, or trigonometric ratios that lie between -1 and 1. You could never have cosine of an angle that is greater than 1 or smaller than -1. So, however, the amplitude of the function would in fact be the distance between the line y equals to 0 and the extrema of the curve. So over here you'd notice that this has a length of 1 unit and this has a length of 1 unit. So the amplitude of the curve would actually be equals to 1. So in fact, it would be as if it's the radius of the range of the function. So an amplitude can never be negative because the amplitude represents the distance from the center of the range to the extrema or the bound of the range. Now over here, sine is in fact an odd function. It's an odd function for a reason that you can actually see that the curve is symmetrical with respect to the origin. So sine is in fact an odd function, and we already know from a previous lesson when we tackled the transformation formulas or the associated arcs that sine of negative x is in fact negative sine x. So if f of x is sine, that would in fact be f of negative x, and that would be negative f of x. So f of negative x is equal to negative f of x for all x in R, implies that the function is odd and the curve would be symmetrical with respect to the origin. Now, regarding the period of the function, now we already know that sine is 2 pi periodic. So in fact, over here, you can actually see that whenever you consider an interval of length 2 pi, when you look at the interval of length 2 pi next to it, you'd actually observe the same curve. For example, if we look here at this interval from 0 to 2 pi, so that is an interval of length 2 pi. If we look at the interval of length 2 pi next to it, which goes from negative 2 pi to 0, you'd notice that this curve here between 0 and 2 pi is the same as this curve here from negative 2 pi to 0. Similarly, you could do so over any interval of length 2 pi. For example, if I consider the interval of negative pi, which is an interval of length 2 pi. So over here, if we actually look next to it, if we consider the interval of length 2 pi next to it, which goes from pi to 3 pi, you'd notice that this curve over the interval negative pi, which over here I will mark by x's, so this curve would actually repeat over pi and 3 pi, and that's because of the periodicity of the function over interval, which is 2 pi in fact. And over here, this last one just is a consequence of the period being 2 pi, which means that sine of x, when you add to x any multiple of 2 pi, sine of x plus 2k pi would actually be equal to sine x, and that's due to the periodicity of the function being 2 pi. Now, if we model the cosine curve similarly, you'd notice that the curve of y equals to sine x looks the same as the curve of y equals to, the curve of y equals to cosine x looks the same as the curve of y equals to sine x. However, the curve of cosine x is in fact shifted by pi over 2 units. You'd notice here that the sine function passes through the origin, while over here for x equals to 0, y is 1, cosine is 1. So over here it's as if the curve was shifted by pi over 2 units. It has the same gradient for all x in R. You'd notice that it keeps the sinusoidal shape and ranges between -1 and 1. Similarly, and in fact the shape of the curve could also be justified similarly to how we did for the sine function. So over here we have cosine to be the axis representing cosine of angles on the unit circle. So over here, if we start with x equals to 0, when x is equals to 0 over here, the abscissa is 1. So this is why cosine of 0 is 1. So for x equals to 0, the function would be 1. And regarding cosine, as you move along quadrant 1, the value of cosine decreases, because over here, don't forget that cosine represents the abscissas of the points. So you'd notice that the abscissas are in fact decreasing. So this is why you'd notice this decreasing behavior of cosine between 0 and pi over 2, and it keeps on decreasing until it reaches y equals to -1. Don't forget, from pi over 2 to pi, cosine is in fact negative in this quadrant. This is why the curve is actually below the x-axis, and at pi over 2 it's 0, and at pi it's -1, and so on. Okay, so when we in fact cover the whole unit circle, you'd notice that at 2 pi, when we have completed a full term, 2 pi goes back to being equals to 1, and at 3 pi over 2 it is in fact 0. And similarly, if we were to go in the negative sense, we would obtain the behavior of the curve for negative angles. So over here again, cosine x is defined for all x in R. So x over here can be any real number. There are no restrictions. So the domain of the function would be all R. Again, y is ranging between -1 and 1. So the range of the function is the interval -1, 1. Again, the amplitude is still 1, because the distance from y equals to 0 to the extrema of the curve is 1 unit to each of the extrema. And however, over here the function is even, because if f of x is cosine, that would be f of -x, which is equals to f of x. So whenever we have a function where f of -x is f of x for all x, it means that the function is even, and you could actually see graphically that the function is symmetrical with respect to the y-axis. Again, similarly to sine, cosine is 2 pi periodic, leading to cosine of x plus 2k pi equals to cosine of x. Now, let's just generalize this a bit. So over here, we just discussed the graphs of y equals to cosine and y equals to sine. However, what if we are dealing, for example, with a function in the form 2 sine of 3x plus 2 plus 1, for example? How could we, in fact, deduce the curve of this function using the curve of y equals to sine x? That is, in fact, because of transformations. Now, we'll discuss that in a bit. So over here, we're just going to define the amplitude and the period for functions in this form. So regarding the amplitude, usually if the function is in this form, the amplitude would actually be the absolute value of the number multiplying the cosine or the sine function. So over here, if it's 2 or -2, then the amplitude would in fact be 2. The curve would actually stretch vertically to have an amplitude of 2. However, if you already have the curve and you need to deduce the equation in order to determine the amplitude, all you have to do is just consider the maximum minus the minimum over 2. Okay, regarding the period of the function. Now, over here, we have that x is multiplied by b. Or over here, we'd have a 3x instead of x. Now, we know that according to horizontal stretches, that if we have f of kx or f of bx, for example, then xy would actually stretch horizontally into 1 over b xy. This is according to horizontal stretches or horizontal dilations. So it's for that reason that the period of this function would actually be 2 pi over b. So if sine or cosine originally have a period of 2 pi, then sine of bx would have a period of 2 pi over b because the curve was stretched horizontally by a factor of 1 over b. However, over here it's very important. I think we're missing an absolute value here. The period is 2 pi over the absolute value of b because the period represents the length of the interval, and the length of the interval cannot be negative. So, and b over here is a real number, it could be negative. However, here it's restricting it to be positive, but in the general case, b could be negative, and in case b is negative, then the period would be 2 pi over b. But however, since we have over here the restriction that b is positive, I'm just going to remove the absolute value. Okay, now the phase shift. The phase shift is in fact by how much the curve was translated horizontally, which you could in fact see here as c. So whatever a real number you add to x, that would in fact represent the phase shift of the function. It's c would represent the number of units that the curve was translated by horizontally, and the vertical shift, so the phase shift could also be denoted as the horizontal shift. Okay, so the horizontal shift is the same as the phase shift, but they do call it a phase in application in physics. So over here, the vertical shift would in fact be d. It's the number you add to the sine or to the cosine function, which if you have the curve and you need to determine by how much the curve was shifted vertically, what you would do is the maximum plus the minimum over 2. However, one last remark that in case a is negative, then the curve would actually be transforming according to all of these transformations, including a vertical reflection across the x-axis. So over here, if this is the sine function, if it's multiplied by negative, the curve would actually reflect with respect to the x-axis. So this maximum would become a minimum, this minimum would become a maximum, etc. So let's just do this example here. We have to find the amplitude, the period, the phase shift, and the vertical shift of this given function. Then we need to sketch it. So regarding the amplitude, that's in fact the absolute value of a, which in fact over here in this case is 2. It's already positive. So for the period of the function would be 2 pi over b, the coefficient of x, which in this case is a 2. So this function has a period of pi. Now regarding the phase shift, the phase shift here is not a 1. In fact, to determine the phase shift, what you need to do is have the 2 factored out inside sine, because over here the phase shift is c when you have it in the form b into x plus c. So over here, this is not 2 into x plus 1. The 2 is just multiplying the x. So in order to determine the phase shift, what you need to do is, in fact, factor out the 2 here. So it's 2 into x plus half, so the phase shift is half. And similarly, we have the vertical shift. So we have the vertical shift. The vertical shift is the constant we're adding to the sine function, which in this case is 5. Then we need to sketch the curve. However, some people could be actually using these info in order to graph or sketch the curve, but I would rather personally do it using the transformations. So if we were to start with y equals to sine x, and then to reach y equals to f of x, how would the transformation happen? If a point is represented by xy on sine x, then what would its transformed ordered pair be on f of x? Let's just start with the ordinates. It's easy. So if sine is y, then what you're doing here is multiplying y by 2 and then adding 5. Then over here, if regarding the transformations on x, if you look at it here, over here we're multiplying by x by 2, and then we're adding 1. We know that operations horizontally on horizontal transformations, they actually reverse. So the multiplication becomes a division by 2, then the plus 1 becomes a negative 1. However, we also know that horizontally the order of operation reverses. So over here, I'm doing the multiplication, then the sum. So here we'd have to do the sum, then the product. So we'd have to reverse the operations. So xy would in fact be transformed into this ordered pair. However, if you were to use this form, then in this case the 2 becomes a half, the plus half becomes a negative half, and you'd notice that over here we're doing the sum then the product, then the order of operations reverse. We'd have to do the product and the sum, which leaves me with half x minus half, which you'd notice that if you expand the half here, you would in fact end up with exactly the same expression for the abscissas. However, in order to graph, now you do know some particular points on the sine, the original sine function. So all you have to do is just transform them. So I'm going to rewrite the transformation here. So xy is transformed into half x minus half, yes, 2y plus 5. So this is the original sine function. And we do have these particular points, which are 0, 0, and then pi over 2, 1, and then pi 0. Did they specify to graph it over which interval? The given is not specifying, but usually they do say sketch over the interval 0 to pi, for example. So let's just do it over 0 to pi here. Okay, so we have 3 pi over 2 negative 1, and we have 2 pi with 1. So this ordered pair would actually transform into, replace here x and y by 0. It would be a negative half 5. Over here, replacing by pi over 2, it would be pi over 4 minus half. And then 2y plus 5, which is 7. Okay, then etc. What you would do is transform, obtain all these ordered pairs. For example, your pi over 4 minus half, you could just determine its approximate decimal value. However, if we did not have the negative half here, just keep them in exact values. For example, if this is pi over 2, pi over 4 would be here. And of course, over here, since we're adding 5, we're having a vertical shift by 5, you'd notice that you'd have to actually extend the coordinate system. So once you obtain all the transformed points, all you have to do is just plot these points and graph the curve, keeping this sinusoidal shape. And over here, since the amplitude is 2, then the curve would actually have a distance of 2 units between the horizontal line passing through half of the curve all the way to the extrema and to the minimum. Now, one last function that we need to discuss here is y equals to tan x. Now, over here, if you look at the domain of the function, it says it's all real numbers except angles in the form 2n plus 1 pi over 2. Now, why is that? So just to make sense of that domain just a little bit, we know that tan x is in fact sine x over cosine x, right? And since this being a quotient of sine and cosine, tan is defined when cosine is different than 0. And we know that cosine x is different than cosine, and cosine and 0 is cosine of pi over 2. Pi over 2 is one of the angles that would in fact have cosine equals to 0. So over here, we have taken in a previous lesson on trigonometric equations that two angles have the same cosine if they are equal or they are opposite. So x is here pi over 2 plus 2k pi, so x would be different than pi over 2 plus 2k pi, and over here it's an and because we want it to be different, not equal, and x would be different than negative pi over 2 plus 2k pi. Now, of course, here where k is an integer, so if we were to consider all angles that satisfy both these conditions, they would in fact be the odd multiples of pi over 2. Over here, you'd notice that pi over 2 is multiplied by 2n plus 1, so here we're considering odd multiples of pi over 2. What does that mean? For example, 3 times pi over 2 is an odd multiple of pi over 2 because we're multiplying it by an odd number. Pi over 2 is an odd multiple of pi over 2 because we're multiplying it by 1. Negative 5 pi over 2 is an odd multiple of pi over 2 because we're multiplying it by an odd number. However, if you were to multiply it by an even number, so that would be 2 times pi over 2, for example, that the 2 would cancel out. We would have pi, and cosine of pi is not 0. So cosine is in fact 0 at odd multiples of pi over 2. So x having these multiples, with these odd multiples of pi over 2 restricted, you notice that in fact the tan function would have at these points, it would have a vertical asymptote. So this is here x equals to pi over 2, that's a vertical asymptote. X equals to 3 pi over 2, x equals to negative pi over 2, x equals to negative 3 pi over 2, etc. So you notice that at odd multiples of pi over 2, y equals to tan x admits vertical asymptotes. However, the range of the function would actually be all r. You'd notice that the range of values of y is in fact a real number. You'd notice that over each interval between every two vertical asymptotes, every value of x has a value of y across all r. Now, we've already seen that tan is pi periodic, which means it repeats every interval of length pi. Now, if we look at this interval, negative pi over 2 is an interval of length pi. So you'd actually see that this being the shape of the curve, over the next interval of length pi, you'd have the curve repeating. So over here, tan of 0 is 0. So this is why over here it passes through the origin. Then after pi units, it would in fact repeat. So this is why you'd notice that the curve actually has x-intercepts at multiples of pi, because tan x equals to 0 would in fact give me sine equals to 0. And sine x equals to 0, 0, one angle whose sine is 0 is 0. So that would be equals to 0. So x is equals to 0 plus 2k pi, or x is equals to pi minus alpha. So x is alpha or pi minus alpha according to the rules we've already seen with the lesson on trigonometric equations. So that would be pi minus 0 is pi plus 2k pi. And these two, we can combine them into one case, which is 0 plus k pi. We've also discussed in the lesson on trigonometric equations that whenever two angles are diametrically opposite on the circle, then instead of taking each plus 2k pi, we can just take one of them plus k pi. For example, this is 0 and this is pi, so 0 plus k pi would actually give you all the possibilities you have here. Instead of just taking 0 plus 2k pi and pi plus 2k pi, you could just start with 0 and move by half terms. So over here, these are the x-intercepts of the tan function. They're the multiples of pi. At every multiple of pi, you'd notice that tan is 0. And tan of pi over 2, these are particular cases to keep in mind. Tan of pi over 4 is 1. We already know through remarkable angles that tan of pi over 4 is 1. And at negative pi over 4, tan is negative 1. Okay, and then of course pi over 4 plus pi, which is 5 pi over 4, also has a tan equals to 1 because tan is pi periodic, and you can actually see that the curve is symmetrical with respect to the origin, which leaves me with an odd function. Now, before we wrap up this lesson, we're going to just go through this problem that models periodic functions. So over here we have Ben, which is a fisherman with a boat in a harbor. This part of the graph that is given here represents the depth of water at the mouth of the harbor. Okay, so the depth of the water at the mouth of the harbor is in fact represented by this function. So you can see it's a sinusoidal function, so it is a periodic function, so it could be modeled by either sine or cosine. So usually sinusoidal functions, if for example, the question does not really specify if you were to model them using sine or cosine. For example, you'd notice here in part 2, they do tell you that this function is modeled by a cosine function. However, usually whenever you have a sinusoidal function, if the question does not specify whether to model it using sine or cosine, you could choose, except the parameters or the coefficients of the function would change if you decided to model it using a sine or a cosine function. So over here, we need to find the amplitude and the period of the function. So over here in part A, we do have that the amplitude, which eventually will be the coefficient, the main coefficient that represents the vertical stretch of the function, is in fact the maximum minus the minimum over 2. So we've noticed that the maxima of the functions are all at y equals to 8, while the minima of the function are at y equals to 2. So it's 8 minus 2 over 2. So I was just thinking that this the difference at the top is a 6. I wrote a 6. So it's 8 minus 2 over 2. So that would in fact be 6 over 2, which is 3. So the amplitude of the function is 3. However, regarding the period, usually periods of periodic functions are denoted by a t. Anyway, so t would actually be, if you had the equation, it would be 2 pi over b. However, here we don't have b. We'd have to determine the period graphically. Now, you'd notice that this is the part of the curve that is in fact repeating. right? So this is one period of the function, and between 10 and 22, the period is in fact 12. So that's deduced from the curve. Now, in part 2, they said knowing that this function is modeled by a cosine function, we need to find the vertical and the horizontal shift. Now, it's important to tell whether this is modeled by a cosine or a sine function, because if we go back just a little bit to the sine and cosine functions, we know that y equals to sine x before applying any transformations has in fact the point 0, 0, a point on the curve. So, however, over here, for example, if I were to just look at this, ignoring that this is y equals to cosine, if I were to model this by a sine function, I'd check for this part of the curve by how much it was shifted. So over here, I'd notice this x-intercept, or I'd look for how many units was this x-intercept shifted, whether to the right or to the left. So over here, if this is the part of the function that actually matches this one on the sine curve, so we notice that it was shifted to the left by pi over 2 units. Okay, well, however, if you know that the function you're modeling is a cosine function, we know that cosine is 1 at x equals to 0. So you'd in fact look by how many units was this extremum shifted. For example, if we look at the sine curve and we try to model it using a cosine function, over here you notice this is the extremum that corresponds to the cosine function. You notice it was moved from here to here. It was moved by pi over 2 units to the right. So then you know that c is pi over 2. So anyway, going back to our word problem. So over here, since we know that it's a cosine function, we would try to locate the extremum of the curve by how much it was translated. Now you'd notice here that this is the extremum of the curve, so we'd need to see by how many units it was shifted away from the y-axis. So over here you notice that from this point to that point we have a plus 4. So in that case, c would in fact be the would in fact be equals to 4, so that is the horizontal shift. Okay, so the horizontal shift, which is in fact c, so that's equals to 4. However, if we're looking for the vertical shift. Now for the vertical shift, it's usually the maximum plus the minimum over 2. It's because we're trying to look for the center of the range of the function. So if the range of the function is in fact all of that interval, so we're trying to locate the center. According to the midpoint formula, it's the sum of the bounds of the interval divided by 2, which in this case it's 8 plus 2 over 2, so it's 8 plus 2 over 2, which is a 5. So the vertical shift is 5. Now over here, to write, by the way, I just would like to point out that the horizontal shift is 4 units to the right. So it's 4 units to the right, which means that when you write it in the equation, when you include it in the equation, you do not forget to reverse the operation. So over here, it's as if we have an x plus 4, whatever y is. So whenever you include it in the equation, it will be x minus 4. So please keep in mind these properties for horizontal transformations. Now we need to write an equation modeling the depth of the water. So over here for more clarity, I'm going to move here, rewrite what we've already found so far. So we have that A is equals to 3, that's the amplitude. We have that the period is 12, and we have the horizontal shift to be 4. Of course, that is to the right. Keep in mind the orientation of the shift, and we have a vertical shift which is equals to 5, and that's, keep in mind that it's upwards. Okay, so if in part 3 the function would in fact be f of x equals to, it's a cosine function, so it's a into cosine of bx plus b, which b into x plus c plus d. Okay, so over here a is 3, of course, so a is 3. Now d is 5, since it's upwards then it's plus 5. Now it's 4 to the right, so that would in fact be minus 4 here, because it's to the 4, it should be x minus 4. And then regarding b, would have to find b using the period. We know that t is 2 pi over b, and t is in fact 3, so that's 2 pi over b. We know, sorry, t is 12. Where did I get the 3 from? I was looking at a. So over here, b would in fact be 2 pi over 12, which is pi over 6. So b is pi over 6. So consequently, f of x is 3 times cosine of pi over 6 into x minus 4 plus 5. So that is the function that is modeling the depth of the water at the mouth of the harbor. Now we need to calculate the depth of the water at 9:30. So calculate that would in fact mean using the equation you just determined, not graphically. So because they said calculate, if they said give, you could refer to the graph and estimate the depth of the water at 9:30. So 9:30 a.m. would actually correspond to x equals to 9.5 on the number line. So over here for part 4, we could just determine f of 9.5, which is 3 cosine of pi over 6 into 9.5 minus 4 plus 5, which is equals to 2.1 meters approximately. Okay, so that is to 1 decimal places. You could just give it to 2 decimal places for more accuracy. Okay, so you would use your calculator to find this. Of course, you're not required to do this without a calculator. Anyway, part 5. Part 5, it says that Ben sleeps till 10 a.m. When he goes out, when can, I think this is when can he goes out. So Ben sleeps till 10 a.m. When can he goes out to the water if his boat can come in and out of the harbor when there's at least 4 meters of water at the mouth of the harbor. So over here it is given that when there is at least 4 meters of water at the mouth of the harbor, Ben can actually come in and out of the harbor. However, it says that Ben sleeps till 10 a.m. every morning. So they need to determine when can he go out according to the function. So since Ben sleeps at 10 a.m. till 10 a.m., then we do not look at any of the times before 10 a.m. because 10 a.m. is when his day starts. So we need to determine, since they said at least 4 meters of water, so we need to determine when is the time after 10 a.m. when the curve is at least at 4 meters, or the point where at least you have an ordinate of 4. So by considering the horizontal line y equals to 4, you'd actually notice that this is the first point of intersection of the curve with y equals to 4 following x equals to 10. So over here, it does not ask you to calculate it. In fact, I'll show you if you had to calculate it, what would you actually do, but the question does not ask you to calculate it. You can just read it graphically, but of course with justification. So over here, if you'd notice, this is approximately at 12:15. So if this is 12.5, this is almost at 12.25, which means it's at 12:15 a.m. So over here, you could say that the curve intersects y equals to 4 at 12.25. You could say over here, in order to just differentiate between the abscissa and the time itself, at x equals to 12.25 after x equals to 10. Okay, so we could say that the curve first intersects, because there are other points of intersection, but it first intersects y equals to 4 at x equals to 12.25 after x equals to 10, then at 12:15 p.m. Ben can go out of the harbor. Now over here, if you were to actually calculate this, you would in fact consider f of x equals to 4, then solve for cosine. So you would in fact have 3 cosine pi over 6 into x minus 4 plus 5 equals to 4. So you would solve for cosine. You would solve for cosine, whatever that value is, and then you'd use the equations of corresponding to cosine. In order to solve for x, then you'd look in the interval given in order to reject or accept values and determine the value of x, the first value of x following x equals to 10. So this is it for trigonometric functions.